Guided media uses physical paths to transmit data. Think of it like water flowing through a pipe. Let's dive into part 1.
Imagine you want to send a gift to your friend. You throw it as hard as you can, but it never reaches him. Now imagine a conveyor belt connecting both houses. Instead of throwing, you simply place it on the belt. It travels safely and reaches your friend. Computer networks work in exactly the same way. Data also needs a proper path to travel. That path is called guided media. Guided media is a communication medium where data travels through a physical cable from the sender to the receiver. Instead of moving randomly through the air, the signal follows a fixed path. Imagine a city without roads. Cars would move randomly, causing confusion and accidents. Roads provide an organized path for transportation. Similarly, without cables, electrical signals spread in different directions. Guided media provides a dedicated path, ensuring the data reaches its destination accurately. Different situations require different cables. Think about water supply. A small house needs a small pipe. A large apartment requires a stronger pipeline. Computer networks follow the same idea. Depending on the amount of data and the communication distance, we use different types of cables. The first type is the twisted pair cable. It is the most commonly used cable in homes, schools, offices, inexpensive, easy to install, and works well for short-distance communication. The second type is the coaxial cable. It has a protective metal shield that reduces electrical interference. Because of this, it provides better signal quality and internet connections. Unlike this cable, optical fiber cable carries data using light instead of electricity. This allows extremely high-speed communication over very long distances with very little signal loss. Now that we've seen the 3 types of guided media, let's begin with the most widely used one, twisted pair cable. More importantly, why are its wires twisted? Let's find out. Let's begin with the world's most commonly used networking cable, the twisted pair cable. Whether you're browsing internet at home or working in office, chances are your devices are connected using this cable.
It is inexpensive, flexible, and perfect for short-distance communication.
A twisted pair cable has 2 main parts. The outer plastic jacket protects the cable from dust. One wire carries the electrical signal to the receiver, while the other provides the return path.
But notice something interesting. The wires are not straight. They are twisted together. Why?
Imagine Rahul and Arjun walking beside a busy road. If Rahul always walks closer to the traffic, he'll hear much more noise than Arjun. Now imagine they switch sides every few steps. By the end of the journey, both have heard almost the same amount of noise. Twisted pair cable works in exactly the same way. As the wires twist, continuously exchange positions.
It allows both wires to experience nearly the same electrical interference.
Nearby electrical devices produce unwanted signals called electromagnetic interference. Because both twisted wires, the receiver compares the two instead of reading just one. The common noise gets canceled, leaving only the original data. This technique is called differential signaling. It is the main reason why twisted pair cables provide reliable communication. The first type is UTP, or unshielded twisted pair. It has no metal shield around the wires. It depends entirely on twisting to reduce interference.
Since homes, schools, and offices usually have low electrical noise, UTP is the most widely used networking cable.
The second type is STP, or shielded twisted pair. In addition to twisted wires, it has a metallic shield that blocks most external interference. This makes it ideal for places with heavy electrical equipment, such as factories and airports. Although STP offers better protection, it is more expensive, so remember this simple rule. If the environment has low electrical interference, UTP is usually enough. If it has high electrical interference, STP is the better choice. But what if we need even better protection? And higher bandwidth? That's where our next cable comes in. The coaxial cable. Twisted pair cable works well for homes and offices. But what if we need better protection against interference and higher bandwidth? For that, we use the coaxial cable. Imagine supplying water to a single house. A small pipe is enough. But what about a large apartment with hundreds of families? A small pipe won't be sufficient. You need a stronger pipeline that can carry more water efficiently. Similarly, when a network needs to carry more data, with better protection, we use a coaxial cable. Let's look inside the cable. At the center is the copper core, which carries the electrical signals. Around it is the dielectric insulator outer shield. Next comes the metal braided shield. This is the most important part. It blocks external electrical interference, protecting the signal traveling. Finally, the entire cable is covered with a plastic jacket, which protects it from physical damage. Unlike twisted pair cable, coaxial cable has a complete metal shield surrounding the signal. This shield blocks most external noise, making communication more stable and reliable. Because of its excellent shielding, coaxial cable is widely used in cable television, broadband internet, and CCTV surveillance systems. So far, all the cables we've discussed carry electrical signals. But what if we could send data using light instead? That's exactly what optical fiber does. An optical fiber cable carries data. It uses light pulses instead of electricity. At the center is the core. Surrounding it is the cladding, keeping light trapped inside. Since optical fiber uses light instead of electricity, electromagnetic interference has no effect on it. It offers higher speed and very low signal loss. Optical fiber is used in internet backbone networks, undersea communication cables, banks, telecommunication systems, and modern data centers. But one fascinating question still remains. If light is traveling inside the fiber, why doesn't it escape through the sides? Let's uncover that secret in the next part. You've just seen that optical fiber carries data using light. But here's something fascinating. Why does it keep bouncing until it reaches the receiver?
Inside every optical fiber are two important layers, the core and the cladding. Whenever the light reaches the boundary between these two layers, something interesting happens.
When light reaches the boundary, three things can happen. If it strikes at a small angle, it passes into the cladding.
If it strikes at a special angle, called the critical angle, it travels along the boundary.
But if it strikes at an angle greater than the critical angle, it reflects completely back into the core. This complete reflection is called total internal reflection, or simply TIR. Imagine throwing a super bouncy ball inside a long corridor. The ball keeps bouncing from one wall to the other, but it still moves forward. Light behaves in a similar way inside an optical fiber. Instead of escaping, it keeps reflecting from the core cladding boundary, moving all the way to the receiver. Electrical cables carry electrical signals. That's why they can be affected by electromagnetic interference. Carries light. Electrical interference cannot affect light traveling inside the fiber. This is why optical fiber provides higher speed, longer communication distance, very low signal loss, and extremely reliable communication. Now we know how light stays inside an optical fiber. But another interesting question remains. Do all light rays travel along the same path? Or can different rays take different routes? The answer will help us understand the difference between single-mode fiber and multimode fiber. Imagine two tunnels. The first tunnel is so narrow that only one car can travel through it. The second tunnel is much wider, allowing many cars to travel at the same time. Optical fibers work in a very similar way. Some fibers allow only one path for light, while others allow many. Before comparing different optical fibers, let's understand one simple term. A mode is simply the path followed by light inside an optical fiber. If light has only one path, it's called single mode. If light has many possible paths, it's called multimode. In single-mode fiber, the core is extremely thin. Because there is very little space, only one light ray can travel through it. This makes single-mode fiber ideal for high-speed, long-distance communication, such as internet backbone networks and undersea cables. In multimode fiber, the core is much wider. This allows several light rays to travel simultaneously. Each ray follows a different path. Some travel almost straight, while others bounce many times inside the fiber. Because these paths have different lengths, the rays do not all reach the receiver together. This delay is called modal dispersion. Multimode fiber is further classified into two types, step index fiber and graded index fiber. The difference lies in how the light travels through the core. In step index fiber, the refractive index of the core remains constant. As a result, the light reflects sharply from the core cladding boundary, creating a zigzag path. Since different rays travel different distances, they arrive at different times, causing higher modal dispersion. In graded index fiber, the refractive index changes gradually from the center of the core toward the edges. Instead of sharp reflections, the light bends smoothly. The rays traveling near the edges move slightly faster, helping them catch up with the rays traveling near the center. As a result, is greatly reduced, providing better performance than DEX fiber. Let's summarize. Single-mode fiber allows one light path and is best for long-distance, high-speed communication. Step-index multimode fiber allows many light paths with sharp reflections, leading to higher modal dispersion. Graded index multimotor guides light along smooth, curved paths. Let's quickly recap. Twisted pair cable is affordable and ideal for homes and offices. Coaxial cable provides better shielding and is commonly used for cable TV and broadband connections. Optical fiber offers the highest speed, the greatest bandwidth, and the longest communication distance using light. Understanding these three guided media forms the foundation of computer networking.